If you look at your handout that I made on page 2, I have a z-test for mean problem. So we're going to go through this. Hopefully you'll understand it by the time we're done. Pardon me, I got to look at the numbers because I did not memorize them and I don't have my calculator in my hand. Here we go. A medical college dean read that the average number of applications a potential medical school student sends is 7.8. She thinks that the mean is higher. In other words, she thinks they apply to more than 7.8 colleges, maybe 8 or 9 or 10. So she selects a random sample of 35 applicants and asks each how many medical schools they applied to. The mean of the sample is 8.7. The population standard deviation is 2.6. And it says test her claim at alpha, so that letter's an alpha, equals 0.01. All right, so she thinks it's more. So in the big picture is we're going to have a right-tailed test. It's more. More means on the right. If I had less, it means on the left. If we say is different, it's split. We'll get to that when we get those examples. All right, things that we know. We know that n equals 35. We know that x bar equals 8.7. And we know that sigma, population standard deviation, is 2.6. And we know that alpha is 0.01. All right, so our first step when we do hypothesis testing is in step 1, we name or we define what our parameter mu is. So mu is the mean number of schools applied to, right? It might be different on my sheet, okay? We also have to write our hypotheses. So we always have a null hypothesis, which is HO, and we have an alternate, the competing claim, which is H1. That's the alternate. I always write the alternate first because that's what the question is. And we said, based on her sample, she thought it was more than what the null hypothesis was, right? So if the null hypothesis is 7.8, so mu equals 7.8, from her sample, we think it's larger than that. So mu is greater than 7.8 is the alternate. The alternate is how our graph looks. So since we said, remember, the alternate is how our graph looks. So when we get to the graph, it's based on the alternate. All right, so step 2 are our assumptions, and these follow the same as what we did for confidence intervals. So what are they? They are, for our assumptions, I'm going to go through these quickly. Letter A, x bar is from a simple random sample. Letter B, n is large. Yep, n was 35. And the rule is greater than or equal to 30. And the third one is sigma is known. So when we know sigma, we use a z-test. When we don't know sigma, we use a t-test, just like with the confidence interval. When we know it, we use a z-test. When we don't know it, we use a t-test. All right, step 3. We need to find this critical value because let's make our sketch and we'll see what that critical value, what it means. So when I get to my sketch on step 4, we'll get back to step 3 in a second. We've got this normal distribution and it's right-tailed. In other words, here's what's hypothesized, that mu right in the middle of that normal distribution. And here's the very right 1%. If our sample ends up on this side, we're going to reject the null hypothesis and say it's wrong. But if our sample ends up anywhere over here, we're not going to reject. So this is the line of rejection. Anything on the other, if it hits the line or is greater, we're going to reject. All right, so we call that a critical value. So what is that critical value? Well, the easy thing is it's on our chart. So if you look at our chart, across the top it says a one-tailed test. All right, so one-tailed test and it's 0.01. You can ignore the confidence interval above that. So go all the way to the bottom, which stands for Z, if you take a look at that. And it says that number is 2.326. So that critical value is 2.326. So I looked at one tail. It's not split, right? I don't have it in 2 parts. I just have a greater than. It's on the right side. And I look at 0.01, because that's the alpha. And I go all the way to the bottom. Okay, go all the way to the bottom, and I get 2.326. All right, so that's my critical value. Are you okay with that? So anything on this side of the critical value, we reject. Anything on this side, we do not reject. So the math behind that is actually a z-score. So z equals our x bar minus our hypothesized mu. That's 7.8. I'm going to write that in. That's just a standard, 7.8 for this problem. All over sigma over radical n. So those numbers again are, let's see, I'm going to have 8.7 minus 7.8. Sigma is 2.6, and n is 35. So let's see, we'll subtract the two numbers on the top. We will divide by what's on the bottom, and that number comes out to equaling, you've seen it before I have, 2.05. So 2.05, that's our test statistic. That's what we call it, that's our test statistic. So that's what the standard normal distribution, the center is 0. Remember, it goes basically from -3 to +3. And this number right here is 2.326, 2.326. So 2.05 must be less than that. It's closer to 0. So guess what? It's going to be around here, 2.05. That's 2.326. These are numbers like 3 and 4 and 5 and 6. Zero's in the center. Okay, standard normal distribution. So we didn't make it. Over here means reject. This side means do not reject. Okay, so I can get to my conclusion now. We are not rejecting. Do not reject. I'm going to write HO. That's null hypothesis. There is not significant evidence. The reason I write significant is because these are called tests of significance. There is not significant evidence to suggest what? To suggest the mean number of schools is greater than, you could say hypothesize, or you can write the number. I'm going to say 7.8. We did not have enough evidence. Not enough evidence here, we don't reject. If we get on this side, if our sample's that far away, if it's that far away, we're going to go ahead and reject. We're saying it's so far away that the null hypothesis can't be true. Okay? So the null hypothesis always ends up 0 in a standard normal distribution. Think about it. If I put a 7.8 in that spot, minus 7.8, I get 0, right? The center of a standard normal is 0. +1, +2, +3, -1, -2, -3. That's review from before. Okay, so that's our first hypothesis test. This is a Z hypothesis test from you. Why do we use a Z instead of T? Because sigma is known. When sigma is known, we use Z. So I wrote out my hypotheses, my assumptions. I found that critical value on my chart. I made my graph, which represents the alternate hypothesis, which was greater. I did my calculation. My test statistic based on my sample, that's a test statistic Z, is 2.05. Hey, it wasn't big enough. So it's on this side, the left side of that line. So I'm not going to reject. Okay, we'll do a few more of these over time. We've got a little time. Enjoy your Easter holiday.